So, to be honest, machine learning and deep learning is one of the hottest topics right now in the market, specifically in the computer science market. And there were problem statements which were deemed to be impossible. Let's say, I guess in the last 5 years itself, which are now possible. Just looking at deep learning and machine learning, and because of the tremendous amount of power computing that they actually have. To name a few, it could be just a basic fingerprint recognition that allows you to actually now access your phone and it's giving you a security feature. It could be a retina scanner. It could be a security camera, maybe built up somewhere in front of your houses that actually allows you to allow people to get in on out. It could be like a face detection system with cameras, to as big as a cell-driven car. All of them together are somehow utilizing convolutional neural networks. My name is Varun Kohli, and I'm a lead strategist for Google, and I come from India. And let's deep dive into convolutional neural networks. But I guess just before speaking about what they are, how they are actually implemented, what are the basic network architectures it has, I guess we should definitely understand the evolution. Trying to identify images or understand what is inside an image has not been an easy task, and a lot of people are actually doing this since a long time, and a really long time. But I guess I'm gonna fast track the entire process and take you through the history where it all started with the first pioneer thing was in 2001. When Paul and Michael actually wrote down a first image, like a face detection system. Back in those days, the chipsets were also not that very smart. They were really very slow, but they were still able to create a real-time face detection system. And looking at that, in 2006, Fujifilms were actually able to launch a camera that actually had a real-time face detection system, which was also one of like really empowering moves in that era. But looking at all of these things, you would have definitely heard today, there was one of the projects called ImageNet that was also evolved in 2006. So to give you a glimpse, in 2006, when so many people were actually trying to solve this problem statement, we didn't have a good set of label data set. We did have label set, but it wasn't enough to actually go ahead and create something really very smart. So in 2006, Master Fei-Fei Li actually started off with a project when she was there in Princeton, and the project was actually named as ImageNet. ImageNet almost got completed by 2009, and by 2009 they actually had 14 million images, and all were labeled with a category set of more than 25,000 object classes, which was really massive. And I guess since then, everybody, like all of us developers, we were literally empowered to actually go ahead and create something really impressive just using that label data set. So since 2010, ImageNet actually started off with a challenge. Every year, they opened up a problem statement saying, if you go ahead and predict, or rather have a bestest image recognition system with the least error rate, that specific algorithm wins. And if you see, all this started somewhere about like 2009, but yeah, there is this slight discrepancy saying, people saying it was 2009 or 10, but the first algorithm that actually got a winning spot was in 2010, and that's there. On the y-axis, you can actually see the error rate that we actually had in those days, and it was pretty high. It was really high. By and by, I guess we've just been doing good year on year, if you actually look at all of the graphs. But there's one thing that you should definitely notice is the year 2012. 2012, we actually had a convolutional neural network, which was the winning algorithm that year, and it was called AlexNet. And if you also see the graph that it actually had beaten in the last year, it's more than 15% on the error rate, which was a really impressive thing. And in those days, it actually also deployed GPUs, which was really fancy in those days. And it was just to actually do a lot of multi-threading. It actually did something really very crazy. I'm sure you should actually go through the paper. It talks about much more than that. Apart than that, in 2014, Google came up with a very fancy algorithm called GoogleNet. If you see the way this has actually been written, there's something hidden about it. We want to definitely cover that. Microsoft came up with a massive convolutional neural network, or we also call that as ConNets, in 2015, which has beaten human beings also at the same time. So let's say if we as human beings have been given actually a set of images and we've been asked to classify that, our error rate on that would be much more than the error rate that ResNet has, ResNet by Microsoft has, which actually got launched in 2015. So I guess this is the evolution, and this is what we are actually moving towards. And on that note, let's try to understand what convolutional neural networks are. Convolutional neural networks are a category of deep learning neural networks. These are slightly away from the standard neural networks that we have, or maybe multi-layer perceptrons, also called as fully connected layers. The reason is all of these layers are actually connected. In a fully connected, all of those, like your input nodes are all connected with your output nodes, which makes your model a bit overfitting. But in case of convolutional neural networks, they actually try to look at how human beings try to identify a particular object. So if we talk about the cortex of a human eye or our human brains, the way it actually runs is that it looks at a particular object and try to classify based on multiple layers. And it's not just going to be like a single image. It classifies into like small bunches in multiple neurons that we have in our brains. It try to classify based on overlapping them and try to understand what that specific object is. And that's how convolutional neural networks have been derived. Okay, so this image signifies something very very obvious, that convolutional neural networks helps you identifying what specifically is there in an image. The use cases could be anything. We just spoke about like a bunch of use cases, but I would actually just suggest that from here onwards, you can assume ConNets are Legos. I guess we all have played with Legos in our childhood. It just could be those building blocks. You could have multiple different colors of building blocks with you, and you could have created something really innovative, something really new, something very different. The building blocks, those Lego blocks here, are a few set of layers. These are 3 specific layers that I actually have mentioned, but it could be a bit more. The first one is the major one here, that's called convolutional layer. There's something called pooling layers, and fully connected layers is just we spoke about. We're definitely going to deep dive into that also. But fully connected layers are again also known as our multi-layer perceptrons. Meanwhile connected to each other. But there's one more thing that's actually missing. All of these layers, there has to be a set of parameters. Because we're talking about neural networks, there has to be parameters. And ConNets offer multiple types of parameters. To start off with, we have kernels, also properly called as filters. There's a discrepancy. A lot of people call them as kernels. Keras calls as kernels, but there are a certain set of algorithms which are familiar with filters. I'm gonna go with filters. I'm much more comfortable with that. We have stride. This is a very different type of a movement that actually comes specifically in images. We'll definitely speak about that. And there's padding. Padding, I guess it's majorly a lot of people understand. Let's say if I'm actually I'm playing outside, I would really need some good padding on my body so that I can save myself from all of those scratches if I fall down, or maybe such kind of things. So there's definitely like a layer over it. That's what we call as padding. But to get it technical, we definitely go onto the next slides. So let's start understanding what convolutional layers are. That's our first Lego block. So right now you actually see a grayscale image of a cat. Assume that's like a 7 by 7 pixels. It's not. I completely agree. But just assume it's like a 7 by 7 pixel. Like how exactly a particular computer would read it would just be numbers, right? So assume all of the numbers that you actually see here, the bigger the number it is, the brighter the pixel will that be. So we spoke about 7 by 7 pixels. You see 49 pixels here. The bigger the number, assume that the brighter the pixel would be there. This might not be like a correct representation, but just still, like say for a moment, we assume that. The next thing that we actually need here to perform a convolution operation here is one of the hyperparameters that we just spoke about. That's the filter. So filters here are the weighted category set that we have in ConNets. Here is exactly the place that decides what kind of feature are you trying to understand from an image. Let's say back in that image of a cat, are you trying to identify the eye of a cat, or are you trying to identify the nose, the whiskers? What exactly is something that's present in that? So that can be done by just like a single filter. Right now we just have like a single filter here. Later down we'll see problem statements we have where we have multiple filters. But just to look at how convolution as an operation gets applied is like this. So for the first block, if you the one in the blue, we actually start doing we start performing like a matrix multiplication, or maybe in a better word would be like a iterative multiplication, where I go ahead and match my filter exactly to the image set that we have. So in other words, it's gonna be 2 into 2, the first block, plus 0 into 1, and I go ahead, like 5 into 3, 8 into 1, 2 into 2, till the moment I get my final number. That's 90. That's how I place it there. And again, for the next one, I would hop one column on the right, and would just go ahead and perform the same convolution. Just by multiplying all of those numbers together, adding all of those numbers together there, I get my number, that's 66. And again, we hop on again at multiple places, the same calculation happens till the time I actually get my entire matrix. Now, if you would actually see, something that's really very creative here is I started off with an image which was 7 by 7, but now I'm lining up with an image which is just 5 by 5. So in other words, you actually had like a bigger image which had so many features, but I have convoluted it. I've convolved it into a smaller set, which is now a representation of a 5 by 5 matrix. And this matrix would actually be now a result of identifying something. The interesting thing here is the size of the output that we actually have. If you look at the formula, that's been calculated by n minus f plus 1. Later down, we're going to just go ahead and add a lot more parameters to this. But yeah, to get started here, n is my size of my input image. So 7 by 7, n is equal to 7 here. My f is the size of my filter, that is 3 by 3 filter that I'm actually utilizing. So my f is going to be 3 and a plus 1. So if I do a 7 minus 3 plus 1, that comes up to be 5, and that's how my output looks like. Just to give you a quick glimpse, my image, when I actually was rolling up my filter over all of the image set that I actually have, I'm not going to cross it over at an image where I just put it partially over the image itself. So in other words, I'm not going to go into such a situation that I start off with 8 and 2 and I don't have a column there. So that's going to be like a negate operation. So we don't go on that part. So in that way, we would actually come across an image set, the resultant image set of a 5 by 5. So I guess in this presentation, I'm definitely going to be utilizing a lot of technologies, tools, but to give you, okay, so just to name a few, I'm going to definitely be using TensorFlow for my last demonstration that I would actually come in. Apart than that, I would be using Google Cloud Platform. That's going to be the basic platform where I would be running my algorithms. I would be specifically using the AI platform that it has. and a few more technologies here. I'm going to show you certain few things on the Collab, and specifically, I'm going to show you things running on Python. The reason is I'm going to show you final things on Python is that you can code these steps if you have understood the methodology in any of the languages. So my pitch here in my entire presentation is going to be that people say that, oh, R is so cool, you should actually write your models on R. No, Python is the best. But I guess my pitch in this entire conversation would be, if you understand the methodology that we are actually talking about here, how convolution as an operation works, you can just go ahead and code it any of the languages. It just could be Perl, which people would haven't thought that machine learning can be utilized. It could be C++. C++ is definitely being utilized. I love it. But yeah. So before we jump on to the code demonstration, I quickly want to specify one thing here is that mathematically the operation that we actually saw is called cross-sectional and not convolutional. So if there are mathematicians here, I'm sure you would just be boggled saying this is cross-sectional and not convolutional. But here in machine learning, theoretically we actually call this method as convolution. But if you want to emphasize what exactly is a convolution operation in mathematics, it's just very similar, but it's just like one more step where you just go ahead and flip your filter almost like by the identity matrix. So anything that you actually see here, so 2 comes up in the last one, but to majorly see this one, so this is my identity matrix, 2, 2, 3. So my 2 would come up here, like whatever value comes up here, 1 gets swapped with 5, so 5 goes up, 1 comes up here. Similarly, 1 and 4. So that's like one step also required, but in mathematics. In machine learning, the process that we actually just saw, that's being called as a convolution operation. Okay, so let's quickly see a few things, how it actually looks like on Collab. Yep, so I'm on Collab. This is like a fairly simple tool. If you haven't utilized it, you can just go on to collab.google.com, it should be somewhere there. I use like an internal version that's slightly different, but yeah. So if you're familiar with Jupyter, it's something very similar to that. You can just get quickly a set of machines there, and you can run entire code there. It's a IPython notebook, so it works very flexibly with Python. This is a fairly simple convolution function that I actually wrote. I'm calling it as convol. Can you see it now? Sure. Okay. Thanks for the feedback. Okay, yeah. So it's a very basic function. Yeah, here it is. It's just going to take a few set of parameters. My apref here is the previous matrix that I actually had. I'm going to input that. The W that I'm actually passing is the size of the filters. B is biases. I'm going to speak about it. And any of the hyperparameters. So in this case, I'm actually not passing any of the hyperparameters, but you would see still of those value being passed because I'm just going to utilize this set of method in like multiple places. And if you actually, so yeah, it's a basic Python code. It's just matrix multiplication or an iterative multiplication here and there, and you finally create a particular matrix. And yeah, that's what I've performed here. If you go ahead and use conv2d in TensorFlow, it's just going to be doing exactly the same thing behind. So that's my pitch here, that if you understand the methodology, you can code it yourself. You really don't have to be dependent on any of those platforms saying, oh, I don't know Keras, or maybe I don't know Scala. So you really don't have to be dependent on it. Just go ahead and understand those complexities, and maybe you can code it out yourself. Yeah, so if you see, this is the exact matrix that I actually had it in my presentation. 2053582, that's my first row, and I had passed down the exact matrix here as my apref and my weighted array exactly here. And if you see, I've passed down my B, that's my bias, as 0. And I'm just calling that specific function. Let me quickly run this. So I'm just calling my code, and I'm going to call this thing. And it results the same specific code that I actually had. I know this sounds lame, but I guess this is just like a small first piece of block, because we are going to go ahead and start building a lot more on this. Yeah. So right now you actually saw a grayscale image, but not necessarily you will always have a grayscale image. You might always have there are good chances that you will always have like a colorful image. If I click a picture right now with all of these faces, it's a colorful image and not a grayscale image. So in a grayscale image, if you see there is only a single layer, in other words, that the size of that image is 7 by 7 by 1, because a grayscale image has a single channel. It's just like white and black, so it has like a single channel there. But in case of a colorful image, you'll actually have multiple channels. So let's look at that. It's exactly very similar what we saw right now, but it just like for a colorful image, there would be 3 channels, red, green, and blue. I haven't shown the red one. I've just colored it with white. But I'm going to apply the same convolution operation, exactly the same mathematical way. But if you see, the resultant says 1. Right? So the reason is, this is how exactly a convolution layer works. The steps that we actually used was only for a convolution operation, but not a complete convolution layer. In a convolution layer, the 3 channels that you actually have, you would have multiplied all of them together, and would have, let's say, in this case, you would have, for the first one, you would have multiplied with 2 by 2 and something, you would have received a number here, 90. But that happens for the red one. You would do the same thing for the green one that is behind it, and that number goes exactly behind 90, and the same thing you do with the blue one. And so you have, in other words, the place that you see 90, you would actually have 3 numbers. And then we actually just go ahead and add a bias to it. A bias gets added to each of these blocks that you have. So let's say for the first block, you'll actually have a like exactly specific bias. Let's say it could just be a number saying 10, right? So you would do that, and you would do a weighted sum of all of those 3 numbers plus the bias that you have, and then you're gonna go ahead and apply a nonlinearity activation function. ReLU in this case. Are you guys aware of nonlinearity activation functions? Awesome. So to the people who actually don't understand it, it just, in basic word, it just a function that allows us to play with non-linear data set. Or in other words, to be very specific, a ReLU function is gonna give me an output. Let's say a weighted sum of all of those values as an input is gonna give me an output of, let's say if it's positive, it's gonna give me give an identity value as an output, and if it's negative, it's gonna give me 0. So in other words, I'm suppressing the values if it's really not very convincing to me. But if it's convincing to me, I'm gonna keep the maximum value. So let's say if of x, I'm gonna get the value. So if of x is positive, I'm gonna x as output, which becomes my identity value. But if my x is negative, it's 0. So if I draw it on the graph, it's gonna be 0 on, if it's negative, if the x-axis is negative, but if it's positive, it's gonna be identity. Okay? So in other words, ReLU is just like a non-linear activation function that allows us to play around with a lot of non-linear data set. That's what we usually have. We're not going to have like a linear data set very soon or easily. And yeah, so this is how we perform it. So given like a 7 by 7 by 3 matrix, I would definitely need 3 channels to multiply it. The way that you saw in the last slide, we went ahead and multiplied it. But here where you exactly see the equal to, the equals sign also actually has a plus of bias, and then performing a ReLU over it. That's why you actually in the end just have one single matrix of 5 by 5 by 1. Okay, and we just saw the formula. The formula remains same. That was n minus f plus 1 by n minus f plus 1. Okay, so let's quickly jump on to something interesting. Now we have multiple filters. Till the moment we were just looking at like a single filter, or maybe in other words, we were just trying to identify one single thing. Maybe in that cat, we were just trying to identify us like the cat's image itself and nothing apart than that. But we would need to to identify a cat. We would also want to know whether that image also has whiskers to confirm whether yes, oh, it's not a human being with a like an eye of a human being. It's a cat or maybe a dog or maybe an animal with a whisker. So to identify that, we would actually have to have another set of filter, right? So in this image, we're just performing the same convolution operation but with multiple filters. If you see in the bottom, you have a red filter and a green filter, or you can call it as like a filter 1 and a filter 2, and you perform the same operation that we actually did, and the resultant gets stacked up here in the final one. And now if you look at the formula of the size of the output, it changes its third dimension, which becomes, the last dimension becomes the number of filters that we actually have applied. In this case, the number of filters is just 2. So our formula becomes n minus f plus 1 by n minus f plus 1 by the number of channels, so the number of filters here, which becomes 2. Okay, let's make things a bit interesting. I'm sure you guys would definitely be aware of this place. I picked this image just because it's a very beautiful building. The architecture is really very nice, but that was not just the sole reason. The sole reason was I wanted to demonstrate to you one single filter that can actually, let's say, identify vertical image, like vertical edges. But if you see now closely on this image, you have so many vertical lines. You have so many doors, not just doors, but at least like a lot of windows there. The entire building, it's really with a lot of vertical lines it has, right? So let's say we actually have this image, this is like a 256 by 256 image, and I pass it down with this specific filter. Now just to recap, the previous slides, whatever the weight that I actually had, that in my filter was junk, was literally passed down for the first time, and was doing something, maybe was not doing anything. But here we have identified this specific filter. This is the exact specific filter that can help you in identifying a vertical edge. And let's see what it does. That's exactly how an image looks like to a computer. If you see now, you would see all of those vertical lines. It has identified all of those vertical lines. But the closer call that you should definitely see is one thing here. This is something that was really very fancy when I was actually looking at. This is not very clear in the image because there is a tree there, and just in front of the tree there is a light pole, because it's straight, a vertical lit, and then on like a bit horizontal, which is not very visible here. But if you see it here, it's really very visible here. So it's easily able to identify those vertical images. Now let's do a quick demonstration. I'm on my Collab again. That's the same method I'm just gonna go ahead and utilize. Just the fancy function that I'm actually utilizing is to import the image. In the first one, I have imported my image. That is, I've called it as, that's the name of my image, and the size of the image is 480 by 480. I'm sorry, in the demonstration I had a 256 by 256 image. Here it's a 480 by 480, but doesn't make much of a difference. I'm plotting my image like this. In actual, the computer looks like a grayscale image exactly like this. So it's a grayscale image, and this is how it's actually able to look like. This is my exact convolution function that I have, that we have written. And I'm just going to pass the same array. If you look at that values, those are the same values there, what we actually had passed. I'm going to quickly come down onto this, why those specific values have been picked up. And if I run it, if you see, I get a 478 by 478 by 1, because I've used a 3 by 3 filter. If I put that into the same formula that we were speaking about, n minus f plus 1 by n minus f plus 1, this is what we would get. And the number of number of filters that we're using is only 1. That's why you'd see the last one here. And the moment I reshape and I print it, this is what I get. So I guess this is your first building block to see how a computer understands or rather looks at an image or like a grayscale image, how the filters actually can behave and can help you identify it. So now let's go back to the slide and talk about those filters. Okay, I'm really running slow, but yeah. So if you look at this filter in the first slide I spoke about, the bigger the number, the brighter it is, right? If I put that analogy here in the filter, that would make the 1 completely as white, 0 that's somewhere in the mid, somewhere as gray, and my last leg that's -1 as black or tinted towards black, right? So okay, yeah. So if you look at it that way, it's gonna be running that entire thing over the set of images, and that's how it's gonna identify vertical sets. But if you want to identify, let's say, horizontal images, you'll actually have to just tilt this image with, put 1 1 1 here on the top, 0 0 0 here, and -1 -1 -1 here, and that way you can identify horizontal images. And similarly, let's say if you want to identify maybe an edge, that's smart, right? I would not have a filter to identify an edge. That's the place where we utilize our garbage values in an input, run our model, and let our model backpropagate and identify which is the lowest minima, and those are the values that where exactly it's able to identify the exact set of image to identify a particular edge. Let's get back. Okay. Okay, so I'm going to quickly run across, we're lacking on time. So padding, so let's say, as I spoke about, padding is something just wrapping around some data set like around it. In this case, I had a 7 by 7 image. For a padding equals to 1, I would pad it with 1 pixel throughout the image, which makes it by 9 by 9. And then if I actually go ahead and perform a convolution operation over 8, my size remains same. It becomes 7 by 7, right? So there are 2 types of paddings that we know so far. One is the valid padding. In the valid padding, I pass down padding value as exactly 0, where I'm actually not utilizing padding at all. So in other words, I would definitely be losing my data set from the edges, because that, let's say that value on the top, that's 2, would just be utilized only for calculating this one, the first pixel, but not in multiple different places. But let's say if I actually start utilizing padding, it would actually help me out in using that specific filter, that value 2, at multiple different places. So in other words, I don't lose my data set. It could be certain set of very important feature which is actually present in those last corner edges, and there are multiple blocks that are actually looking at it so that I don't miss it. So yeah, that's what we do specifically in padding. Okay, I'm going to skip on the code demonstration. I'm really sorry. Okay, so stride is my next really important hyperparameter. Here, let's say the same given 7 by 7 image with a 3 by 3 filter. If I actually do a strider 2, for the first set of image, I would, for the first block, I would do the same scale of convolution operation. Sorry. But for the next one, I'm going to hop 2 columns, because my stride value is equals to 2. For the next one, when I go a column down, I'm gonna jump 2 columns down. So whenever I'm actually looking at a different block, I would be jumping my columns and my rows with the value of stride that actually has given. So here in this case, it's stride equals to 2. That's why I'm hopping 2 columns or 2 rows. In a case when my stride is equals to 3, I would jump 3 by 3. But if you look at the size, a 7 by 7 image has actually reduced down to a size of literally 3 by 3. And here the formula changes. Now my formula is n plus 2p minus f. I've introduced padding. Padding is p here by s and plus 1. So we are dividing by s because if you see, we are jumping so many numbers here and there. Okay. I'm really sorry, I'm jumping on the stride demonstration. It's the same thing, I just actually have to tweak on those values and you would get the same result. Okay, so pooling layers. We have two types of pooling layers, max pooling and average pooling. In the same, let's say given 7 by 7 image, if I go ahead and perform a pooling, my pooling layer does not actually have a weighted value. It would just go ahead and look at like a given 3 by 3 filter, will just find out a maximum value within that set. So let's say in this particular set, whichever is the maximum value gets associated here. And I jump on, let's say, 2 columns because my stride value is equal to 2. And I just go ahead and perform the entire value till the moment I had the entire matrix. In case of average pooling, what we just do is exactly the same. In the first block, now we start looking at the average value of the entire thing, and we can just go ahead and identify that. So writing that code is really very easy. I really don't think you need very fancy tools for that. Yeah, maybe you can definitely try that out. I'm skipping my demonstration this time, just in case, because I wanted to show you the final one. Okay, so fully connected layers. I'm not going to push on a lot more on this one. The reason is because these are the multi-layer perceptrons or the neural networks or the fully connected layers that you would have definitely known or studied in deep learning if you have ever worked on it. But in case, let's say I actually have a 4 by 4 by 3 image, which looks like this. So 4 by 4 by 3 is going to be 42. I would flatten out all of those 42 values in one column, and then I'm gonna go ahead and identify or connect it to all of those perceptrons that I actually have written. Let's say 10 in this case. So let's say if the first one gets connected with all of them, the second one and the third one, and till the last one. To give you more glimpse, all of those edges that you actually see here would actually have a weight, like the weight we saw in filters. That gets applied, and along with that, a bias is just also going to be added up to all of these values. So in this case, we're going to have, we have 42 by 10 weights and 10 biases. So that's going to be, that's how you actually also calculate the number of parameters. But if you look at the number, it's really massive. We just spoke about 42 into 10 with just like a single layer. And we're just gonna go jump and multiple places. This is like a single fully connected layer. We would definitely have multiple here. But yeah, in the end, let's say you can have more layers here, but I'm actually putting a softmax layer. A softmax is again like an activation function. It's gonna help me out in identifying the maximum value. I'm gonna suppress the other ones, but it's not just gonna nullify them, so that let's say even if my model is identifying something wrong, it's gonna keep it there. It's really not gonna miss it there, so that I can come back and actually identify them. So you can also assume it to be like a classifier that's actually been written in the end, saying just 0 or 1. Could just be taken, let's say maybe as somebody said, like a spam or a not spam, maybe like a virus or a not virus, or like a cat or a dog, or yeah, any of those classifications there. Okay, so now we're jumping on a few architectures. This is something that I really want you to have a look at it. The reason is because writing your own convolutional neural network architecture would really not make sense, because these researchers have spent years and years in identifying those specific architectures. And we researchers have always seen this process that we can actually just go ahead and take a binge on all of these algorithms or architectures, and these architectures really work well in multiple places. So you don't actually have to invest so much of time in creating your own architecture. You can have a look at it. PlayNet, to be specific, was the first convolutional neural network that was actually written in '98. And that was specifically written to identify a handwritten number. So that also makes us understand, like very obvious that the resultant is going to be 10 values in the end, which is going to be classifiers from like 0 to 10, 0 to 9. Yeah, so let's look at it. So given image, my 32 by 32, if you look at it, it's like a grayscale image. That's a single reason that it has one channel. I'm going to pass it down with, I'm going to pass it down with 6 filters of size 5 by 5, and I'm going to put my stride as 1. If I go ahead and start applying the same formula, n plus 2p minus f by s plus 1, and my number of channels here, the channels is 6, I'm going to get this. So that's like 28 by 26. Now, in those days, people were actually applying average pool. average pool, now nobody actually usually looks at it. The reason is because average pool is going to give you an average value, but let's say if there is a feature available in that set of box, and you do an average of it, there are chances that you might miss it. But if you do a max of it, that value is not gonna, like, you're not gonna miss it. So that's why, like, in these days, a lot of people use max pooling and not average pooling. But yeah, back in those days, people used average pooling. If you also see, we had a stride equals to 2 and a size by 2 by 2. That's why our the image chunked exactly by 28 by 28 by 6 to 14 by 14 by 6. And yes, we again go ahead and apply a convolution layer of 16 filters, size 5 by 5 and 1, and we get it like a 10 by 10 by 16 image set. And we again apply an average pooling. The image size reduces exactly by 5 by 5 by 16. Now is where we actually apply our fully connected layers. So yeah, 5 by 5 by 16, that's somewhere about like 420. I flattened them up exactly there. I'm not showing that layer here, and I'm mixing them here with those 120 neurons, and all of those 420 would be joined here with 120 here. That becomes my set of parameters just for this fully connected layer. I would again apply a fully connected layer, and to the final where I have my y. In those days, softmax was not utilized. My y value there was like a basic classifier from 0 to 9 to identify whether what exactly this number is. So let's say in this case it's going to be 5. Yeah, so just few things more here, that in those days we were not using ReLU. We were using linear functions like non-linear functions like sigmoid, which is not again utilized in these days. But if you see, the sigmoid was actually applied long after. Okay, so I'm going to skip most of it so that you can actually look at something really interesting. I'm really sorry, I just have 3 minutes. Okay, so I actually wrote down, okay, maybe I'm going to move across. Okay, so that's AlexNet. At least you can actually definitely have a look at it. Yeah, that's GoogleNet. What I'm actually demonstrating is something very similar to this. That's how exactly GoogleNet looks like. It's something written on Inception. There is a fun fact associated to it. If you had seen that movie, we do need to go deeper. Okay, so yeah, that's where my final demonstration is. I've written like an airplane detection system that actually looks at Google Maps API images and goes ahead and classifies them whether it's looking at a plane or not. And it's like a bigger layer of object identification also being written on it, so that it can actually put down a box over it. The dataset that I actually have utilized is PlanesNet. That the dataset is open available on Kaggle. I would have it here. Yeah, so the dataset has like close to 8,000 images of planes, 10 by 10 pixels, or 20 by 20 pixels, and some 24,000 of junk images which look similar to a plane but are not. So that's my classified dataset that I actually have utilized. I'm using Google Cloud Platform as my architecture because I definitely wanted GPUs. I cannot run this model. This specific model is running on close to 12 million parameters. It's going to be really extensive if I'm actually running it on a CPU. It's going to take a week or maybe more. I haven't tried that. But yeah, so this is something that I actually had executed on Google Cloud Platform. I used AI Platform. Yeah, ML Engine is now AI Platform. I can scroll down here and that's my dashboard. Yeah, but yeah, so that's one of the models that I actually had written. But if you could see, that got executed in 25 minutes. Yeah, that's how it actually had performed. Yeah, 30 minutes to be specific. Okay, so just one more thing. I actually had utilized, I had created a front end associated to it. I borrowed a front end associated to it from Martin Garner. He's one of the very famous data scientists. So the model that I actually had written had to look at the images that are actually available. Let me quickly show you a quick demonstration. So I'm running an HTTP server on my laptop so that you can actually have a look at it. That's how it looks at it. I'm authorized, I'm signed in. Just need to pass on my name of the model. That's the name of the model. So if you want to go ahead and look at more technical details around it, this is a particular project that I actually had created, like the Google Cloud project that I had created, then a slash the specific model and the specific version. So here what you're actually looking at is I can actually hover down from multiple images from multiple airports. Let's say if I'm actually looking at an airport image from Los Angeles, that's how it actually looks like, and blah blah. So the moment I click analyze, it's gonna run and it's gonna go ahead and identify images over it, like identify planes over it, and it's gonna go ahead and draw boxes. It's gonna be slightly slow because this is the first version. I'm running it on like a single core. I have a second version which I'm actually running on quad core, but that's still in like test phases. Yeah, it should just be somewhere here in a couple of minutes. Yep. So meanwhile, what I actually want to mention here is when I actually had created that model is, yeah, a few things are not there. Yeah. So it's going above the capacity. The reason is because it's running on a single core, but the one that's gonna go ahead and execute is gonna still put down boxes if there are. Yeah. So if you could still see boxes there. The red one justifies that there was so much of data set that was given to like a single layer. It couldn't process it within the given time. But yeah, I can move around. So if you could still see, there are the planes that it could identify and actually had created boxes over it. Similarly, I can actually just go ahead maybe with Tokyo's airport and just perform the same thing here. Yeah, this is quick. And yeah, if you could see it here, I guess it has done a good job. I'm sorry, I hovered it. Yep. The efficacy of this model was really nice. I guess it was outperforming close to 97% in terms of recall, and again some 96% in terms of its precision. It would identify maybe a few things which are very similar to not planes. The reason is because the data set that was given to me was just white color planes, but there are certain set of images which are, let's say, are like colored planes or like colored images here and there. So that's why you see certain images, like certain more blocks here and there. Awesome. Okay.